Welcome to The Explainer. Today we're diving into a really fascinating paper by author Mathis. It's a piece that takes a hard look at our most basic understanding of water and proposes a pretty radical new theory to explain some of its strangest behaviors.
You know, what's interesting is that the paper doesn't start with a takedown. It actually begins with a nod of respect to Dr. Gerald Pollack, a scientist whose own work on a so-called fourth phase of water has already made plenty of waves. The author basically tips his hat to Pollack for being brave enough to challenge the status quo, even as he's about to challenge Pollack himself.
So here's our game plan for this explainer. First, we're going to look at Pollack's theory of a mysterious fourth phase of water. Then, we'll get into the author's alternative idea, something he calls charge channeling. After that, we'll see how he uses this idea to tackle some old scientific controversies. And finally, this is the really wild part. We'll see how it could completely redraw the water molecule as we know it. Okay, so let's start with Gerald Pollack's work. It all revolves around this phenomenon he discovered called the exclusion zone, or easy water for short. This is the foundation for his whole theory. So what happens when water comes into contact with a surface it likes, a hydrophilic surface? A very strange, ordered layer of water forms right next to it. This EZ water actually pushes things out like tiny particles, and it's thicker, almost like a gel. It's from observations like this that Pollack came up with what he calls 4 new rules of nature. And here they are, the 4 big ideas from Pollack, as laid out in the source paper. He's proposing that water has a fourth phase, not just solid, liquid, and gas, that it can store energy from light, and maybe the most controversial one, that things with the same charge can actually attract each other. But the author we're looking at today argues you can throw all 4 of these out and replace them with one single, much bigger idea. And that brings us right to the heart of this paper. It's an alternative theory the author has developed, and he calls it charge channeling. This slide really frames the whole argument perfectly. On one side, you have Pollack's view, 4 brand new rules just to explain the weirdness of water, and on the other side, you have this author's view, one single rule, one mechanical theory that he claims explains not just water, but, well, everything. So what on earth is charge channeling? Okay, the paper says you have to stop thinking about charge as this invisible, abstract property. Instead, imagine it's a physical thing, a literal, constant wind of photons that is always flowing through and around all matter. And atoms and molecules, they're like little pipes or channels that this wind flows through. So if you look at things from that perspective, this idea of a physical charged wind, the author says Pollack's rules start to look different. He argues that Pollack saw the effects correctly but misunderstood the cause. For example, water doesn't store energy from light, it just restructures itself to become a better, more efficient channel for that photon wind that's always there. Now the author doesn't just leave it there. He takes this theory and puts it to the test, using it to try and solve a couple of old scientific mysteries that have been pretty much ignored by the mainstream for decades. He hones in on 2 big ones, the polywater controversy from the 1960s and the whole water memory debate from the 80s. The author's claim is that both of these phenomena were probably real, but they got shot down and buried because they just didn't fit into our standard understanding of physics. His take on polywater is that it was real. It just had the wrong name. He says that when scientists forced water through those super thin tubes, they were actually forcing the water molecules to line up, making them way better channels for this charged wind. That's what made the water thick and syrupy. It wasn't a polymer, it was charged water. Now, of course, there's the official story. The mainstream explanation, which the author pulls right from Wikipedia, was way less exciting. The experiments were just sloppy. It was claimed that polywater was nothing more than regular water contaminated with stuff sweating off the scientists' hands. But the paper is deeply skeptical of this. The author basically asks, are we really supposed to believe that these highly trained scientists in labs all around the world all made the same basic mistake, that they couldn't tell the difference between a revolutionary new form of water and salty sweat? It just doesn't add up for him. And he applies a similar mechanical logic to those water memory experiments. The idea here is that when you dissolve a substance in water, it creates specific pathways for that charged wind to flow through. And under the right conditions, those pathways, those charged tunnels, can actually stick around even after the original substance is diluted so much that it's completely gone. And here's the kicker. The author points right back to Pollack's own experiments as proof. In one test, tiny beads were being pushed away from the easy zone. Okay, but then they reversed the electrical charge of the beads, and they were still pushed away. The author argues that's impossible under standard theory. It only makes sense if charge is a physical wind that is literally blowing the beads away no matter what their polarity is.
All right, and this is where it gets really mind-bending. The paper takes this whole charge channeling idea and applies it all the way down to the quantum level, proposing a completely new way of looking at the water molecule itself.
We all learned about that famous 104.5-degree angle in a water molecule, right? Well, this paper argues we've been measuring the wrong thing. It's not an angle between the hydrogen and oxygen atoms, no. He claims it's the angle between the primary streams of charge that are flowing through those atoms.
So how would that even work? Well, he lays out a mechanical model. It starts with the idea that the Earth's ambient charge field isn't perfectly balanced. This imbalance supposedly pushes the hydrogen atoms into a lopsided arrangement around the oxygen. And it's that physical asymmetrical configuration that mechanically creates the famous bent shape of the molecule.
Okay, but what happens when that water molecule gets really close to something with its own strong charge field, like one of those hydrophilic surfaces in Pollak's experiments? The argument is that the strong local field can overpower the Earth's background field and basically yank the water molecule straight. And here's the punchline. A straight, symmetrical water molecule is a much, much better conductor for that charge wind. And that, the author claims, is what easy water or structured water really is. It's not a new phase, it's a new shape.
The author then circles back to the polywater debate with a pretty bold jab at the famous physicist Richard Feynman. See, Feynman once quipped that if polywater was real, some animal would have evolved to take advantage of it. The authors come back. That animal already exists. It's called a plant. Plants use narrow tubes, capillaries, to create what he calls charged water all day, every day.
So we've walked through a really radical theory here, one that reimagines one of the most fundamental concepts in science. It redefines charge not as a property, but as a physical, moving field of particles. And it leaves us with a really provocative question to think about. If our fundamental model of charge really is incomplete, what else in physics, chemistry, and even biology might we have completely wrong?